Hi everyone. This is going to be a lesson for linear algebra about applications. I've decided that the application that I'm going to focus on for this lesson is 3D graphics. So, linear algebra can be used for a lot of things because just solving systems in general comes up in a lot of different areas. A system can represent something from business or science or engineering. So solving systems of equations is important, but the application that I decided to focus on, this is going to be more of an application of linear transformations and matrix multiplication. So let's take a look at 3D graphics. All right, so let's take a look at what role linear algebra plays in 3D graphics. First of all, I want to start with a quick intro. I want to say that in 3D graphics, linear transformations are used to rotate, scale, and move objects. This is used in movies, video games, etc. TV shows, advertisements, all sorts of things. Remember, every linear transformation which we could call t from Rn to Rn. I guess we're going to be focused on this kind of square case where we're going from Rn to itself. So the domain and codomain are the same. Every linear transformation can be represented by a matrix. So we could say that t of x equals ax. There's always this matrix A that we can find, and earlier in the semester we talked about how to find that matrix A. If you're given a linear transformation as like a formula, we know how to find the matrix that it corresponds to. So in this lesson, we'll discuss 2D and 3D. So really, the application that I want us to learn about is three-dimensional graphics, but a lot of times it's easier to illustrate the 2D case. So what we're going to do is we're going to look at the 2D case for rotation and scaling and moving objects, and then we'll see how do you extend the 2D case to turn it into 3D. So let's start by talking about reflections in 2D space. So, reflections would be flipping an object around, and we'll say that a two-dimensional image, instead of a three-dimensional model or a three-dimensional shape, just a two-dimensional image or shape is made up of points x comma y in R2. We can write them as vectors, or we can write them as ordered pairs. So suppose we want to reflect across the x-axis. And I'll draw a picture of this. This is easy to draw because it's only two-dimensional. So we have an x-axis, a y-axis. Let's suppose that we have a picture that's in quadrant 1, and I want to reflect it across the x-axis. The way that I'm going to depict this, my picture that's in quadrant 1, I'm just going to kind of draw it as a box. And I'm going to put the letter P, for picture. All right, so that could be some kind of image, and we want to reflect it across the x-axis. So what would that look like? That means that we want to flip it this way, vertically, and it's going to wind up in quadrant 4 and look something like this. A mirror image of itself where the x-axis has kind of acted like a mirror. So what is the matrix of this transformation? You know, I claim that this is a linear transformation, so it should have a matrix A. Remember, when we are given a linear transformation as a formula, the way that we would find the matrix A is we would look at how does the linear transformation act on the elements of the identity matrix, or I should say the columns of the identity matrix. In other words, how should this act on the basis vectors of R2? You can call them the columns of the identity matrix, or you can call them the basis elements of the space R2. It's going to be this vector and this one. If we can figure out how this transformation should map these two vectors, then we could figure out the matrix A of the linear transformation. Oh, by the way, since we are talking about this as points x comma y, we could say that this first vector, we could think of it as a point 1 comma 0, and we could think of this one as the point 0 comma 1 in this picture. So, you know, we basically say, how should the transformation act on those? And I guess we'll call the transformation T. I didn't really say that anywhere, but we'll call the transformation T, and we'll call the matrix of it A. So let's look at this point 1 comma 0. That's going to be over here. So if we want to apply this reflection transformation to the point 1 comma 0, what should that get mapped to? I mean, geometrically or visually, we want to flip it vertically, or I should say we want to reflect it across the x-axis. Well, this point is already on the x-axis, so it doesn't go anywhere. It doesn't go anywhere, right? Take this, reflect it across the x-axis, it stays right where it is. So you could also think of that as a column vector like this. All right? And what about the other one here? Let me draw a little dividing line here. What about the other vector? The other basis element of R2. That is over here. The point 0 comma 1 is up here. And if we reflect it across the x-axis, it should move down to here. So T of 0 comma 1, this one actually does move. When it gets reflected, it becomes 0 comma negative 1. Or writing it as a column vector, 0, negative 1. So we've seen how this transformation should map the basis elements, or the columns of the identity. So we know what the matrix A is. Let's write this result. So the transformation, it goes from R2 to R2, where T of x equals AX with A equal to, remember, we just take these two vectors that we found. So 1, 0, and 0, negative 1. That's the result. That is the linear transformation that would perform a reflection across the x-axis in two-dimensional space. Not just of the basis elements, but of any vector that you put in. So if you put in a set of points, put each point into this transformation, and they all will wind up getting reflected across the x-axis. We could do similar work to figure out the matrix for reflecting about the y-axis, but let's just focus on this one for now. So how do we extend this to reflections in three-dimensional space? Okay, I'm going to have to draw some three-dimensional pictures, so bear with me because that's a little bit tougher. First of all, let's say that in three-dimensional space, points are x, comma, y, comma, z in R3. And we could reflect them in lots of different ways. You know, when we were talking about two-dimensional space, we could reflect about the x-axis or y-axis. But in three-dimensional space, there's more options, right? So I'm going to choose one for us to focus on. Let's say that we have a three-dimensional set of points, which could be describing some kind of object, and we want to reflect across... Let's reflect across the YZ plane. And I'll draw a picture of this, or I'll attempt to draw a picture of this. All right, let's see how my picture goes. All right, so here's my picture. We are starting with an object over here. You know what? I'll zoom in on this picture a little bit. There we go. So we have not just the XY plane. You know, we've got three-dimensional space here. So we have an x-axis, a y-axis, and a z-axis. And we have some object which I drew in black, and this is sort of the original object, and we want to reflect it across the YZ plane. So you could see that Y and Z kind of create a plane, and I'm reflecting this across that. And, you know, if we say the YZ plane is kind of acting like a mirror, and this is getting reflected through it. So, yeah, the object winds up over here. And we want to talk about what is this linear transformation. So we'll do this with the same kind of strategy we did earlier, which is we will look at what should this transformation do to the basis elements. The basis elements of R3 would be 1, 0, 0, 0, 1, 0. I'm not going to draw a picture for each one of them this time. All right, so if we're reflecting across the YZ plane, and these are x, y, z, then this should get sent to -1, 0, 0. This should get sent to 0, 1, 0. This one doesn't move because it's on the axis that we're reflecting across. And then the last one also doesn't move, 0, 0, 1. So we can write this out as the standard matrix of this linear transformation, but I want to point out to you that the sign of the x-coordinate flips. Right, that happened here. And the other coordinates are unchanged. That's kind of what it means to reflect across the YZ plane. And T of a general XYZ would get sent to -XYZ. I mean, that's the same thing I just said in that sentence. I just wrote it out. And the standard matrix of this linear transformation from R3 to R3 is A equals Well, it has to be a 3 by 3 matrix, right? You just take these three vectors that we found, write them as column vectors. So -1, 0, 0 was the first one. 0, 1, 0, 0, 0, 1. All right, and if you were reflecting in a different direction, then you would have a minus sign in a different spot. So yeah, you can reflect a point by multiplying this matrix times that point. And if you have an object, you could just treat it as a set of points and multiply each of them a times x. You know, a times your vector, and it will reflect your object. So reflections are one kind of transformation. Let's talk about scaling. Scaling, and we'll first start by talking about it in two-dimensional space. And then we'll talk about the 3D version. So suppose an object is centered at the origin. And we want to enlarge it. I'll draw a quick picture of this. In the two-dimensional case, we have the XY plane. Let's draw just a box. You know, that's kind of what I did originally. I think I wrote a box with the letter P in it, so maybe we do that again. So let's say the object that we want to scale is some kind of picture or set of points that is centered around the origin. That's my original object, and I want to scale it so that it becomes this large. And we'll talk about how can this be done with a linear transformation. All right, so all these points kind of expand outward. Actually, we could label some of these points, can't we? Like this point here would be the point 1, 1, and it looks like it gets moved to the point 2, 2. What's the mapping on the basis vectors? In other words, what's t of 1, 0, and what's t of 0, 1? Because we'll figure out the standard matrix for the transformation based on that. And I'm supposing that I want to enlarge it this much. So I want, you know, a box of this size to become a box of this size. Well, 1, 0 is actually a point that's on this square that I drew, right? 1, 0 is right here, and it looks like it gets moved over to 2, 0. So 2, 0. 0, 1 is also a point on my box, and we can see from the picture that it gets moved to 0, 2. So the standard matrix of this linear transformation seems to be 2, 0 as the first column, 0, 2 as the second column. And yeah, any kind of set of two-dimensional points that you have centered at the origin and you want to expand, I guess, by a factor of 2, you wind up using... Oh, I'm sorry, I wrote standard basis. I meant standard matrix. The standard matrix of this transformation. All right, so we were enlarging by a factor of 2, and we wound up with some 2's in there. So let's just say, more generally, in general, t of x equals ax, with a equals, let's say we want to scale by some other amount. It wouldn't just be a 2, right? We could call this k0, 0, k. How about that? And I'll say that we use k greater than 1 to enlarge, and we use a k between 0 and 1 to shrink. So those are the two types of scaling that we might want to do. Notice that if k equals 1, then you just wind up with the identity matrix, and that doesn't really do anything, right? If you multiply something by the identity matrix, it doesn't change. So this describes how you would scale things centered at the origin. A little bit later, we'll talk about how if something's not centered at the origin, then you might be able to move it so that it is centered at the origin. Let's also talk about scaling in three-dimensional space. This time, I'm not going to draw a picture of this. You could probably visualize it. Just imagine, maybe a cube or a sphere or something like that centered at the origin, and you want to either enlarge it or shrink it. And we could use a similar strategy to what we did above. So that's why I'm just going to say similar to above. You could figure out what it does to the basis elements. But this has to be a 3x3 matrix, and it's going to be this matrix. Looks kind of like the identity matrix, but instead of ones, it has a different constant there. So far we've talked about reflecting objects and scaling objects. That might be helpful in 3D graphics. A really important one, or a really interesting one, is rotations. So let's start by talking about rotations in two-dimensional space. And we'll do the two-dimensional version first, like we've been doing, and then we'll get to the three-dimensional version. Let's start by saying, suppose we want to rotate an object. Let's say 45 degrees counterclockwise. This is just one example of rotation. And let's say we will do this pivoting around the origin. Because when you rotate something, you need to kind of have a pivot. So I'll draw a picture of this. In fact, I think I'll draw this one as two separate pictures. All right, first I'll draw kind of the object that we're going to start with, and then I'll draw the result that we're trying to achieve. This is two-dimensional. We've got the x-axis, y-axis. Let's do this with the same kind of object we started with in that first example, where we just have kind of a square with the letter P in it, where this could be like a picture, right? It could be a two-dimensional image. It could be a photograph. Or it doesn't have to be. It could just be a box. It could be some other shape. This is our example. What we want to do, if I want to rotate this 45 degrees counterclockwise, and I'm using the origin to kind of pivot around, I could actually just rotate my paper, right? Rotate my paper 45 degrees. That's what we're trying to do. But let's draw this on the XY plane, and all right, here's one. We'll do the same kind of scale. You should wind up with something like that. We rotated, and this is the result of rotating 45 degrees. So here's what I'm going to say at this point. I would like you to try it. I would like you to find the matrix of this linear transformation from R2 to R2 Similar to what we were doing earlier, think about what should it do to the basis elements. And from there, you can find the matrix. So I'd like you to pause the video and try this out. Okay, we need to find out what it does to each of the basis elements. So here's what I'll do. I'll separate this off. First, we'll talk about what should it do to 1, 0, and then we'll talk about what should it do to 0, 1. Here, I'll draw a quick picture of this. Let's see. Here's the point 1, 0. Where should this point go if it's being rotated in this way? So we're pivoting around the origin and we're rotating 45 degrees. It should move this way and wind up here. Right? It's kind of moving along the unit circle if you think about it. Like here's the unit circle. And you know that when you learned about the unit circle, usually you went counterclockwise. And this 45-degree rotation takes us to one of the common points that we know on the unit circle, square root of 2 over 2, comma, square root of 2 over 2. That's a 45-degree rotation. So yeah, that's going to be the destination point. That's what this should get mapped to. Look back at the picture up here. Can you see that we had the point 1, 0 as one of the corners of my square? And look where it wound up. It wound up floating around right here. And yeah, that's the point square root of 2 over 2, comma, square root of 2 over 2. For the other point, we're talking about something that starts at 0, 1. So up here, and it's being rotated that way also, winds up over here. This is also kind of moving around the unit circle in a sense. And this is going to wind up at negative square root of 2 over 2, comma, square root of 2 over 2. It's a 45-degree rotation. So the answer to this question, that was my work. And the answer is a 2x2 matrix that looks like this. All right, so it seems like that was very specific to a 45-degree angle. And if we were rotating some different amount, then we would have different points here. So let's talk about that. What about rotations more generally? What if I wanted to rotate 30 degrees or 60 degrees or 90 degrees? So in general, to rotate counterclockwise about the origin, through an angle, theta. The linear transformation goes from R2 to R2, where T of x equals AX, with A equals. All right, we're being more general here. We have an angle theta. So it seems like 45 degrees got us, to this point on the unit circle. If you think about it, back when you learned about trigonometry and the unit circle, you learned about going around the unit circle and getting to some kind of terminal point, and it has an x-coordinate and a y-coordinate. These correspond to cosine and sine, don't they? Isn't the cosine of 45 degrees equal to the square root of 2 over 2? and the sine of 45 degrees is equal to the square root of 2 over 2. Here, you know what? Let's write this. Let's write 45 degrees. Yeah, this is sine and cosine. So actually, the first point that you wind up getting is cosine because it's the x-coordinate, and the second one is sine. And over here, we got negative sine theta and cosine theta. And this would be slightly different if you wanted to rotate clockwise. You know, I said counterclockwise. But yeah, that's the general way that you could do a rotation by any angle. You could rotate by 10 degrees, 11 degrees, whatever you want, as long as you use this matrix. Maybe if you have like an object, we'll talk about the three-dimensional version of this next, but maybe if you imagine you have some object you want to rotate gradually, like you're doing an animation of something, you know, slowly rotating, then maybe the way you would do it is maybe you would rotate it by 1 degree, and then rotate it by another 1 degree, 1 degree, 1 degree, and just keep doing that, right? So you would set up your matrix and just keep multiplying by it. Let's talk about rotations in three-dimensional space. I'm not going to draw a picture of this, but it's similar to what we just did for the two-dimensional case, except now we rotate in the xy plane, xz plane, or yz plane. So it's kind of like we need to specify the angle, but also the direction, you know, in which of these planes are we rotating. So it's actually a different linear transformation depending on which one of these you're doing. And I'll tell you the standard matrices for these. So this first one, cosine theta, sine theta. This is a 3x3 matrix, but it actually starts off looking like the 2x2 matrix we had above. The rest of the entries are 0, 0, 1, 0, 0, 1. That's for rotating in the xy plane, a three-dimensional set of points. Over here, cosine 0, sine 0, 1, 0, negative sine 0, cosine. You could verify these by thinking about what it does to the basis elements. But I'm just saying it's similar strategy to what we did above, so I'm not showing every detail. All right, those are the standard matrices for rotations in three-dimensional space. If you want to if you want to rotate in more than one of these, like let's say you have an object that you want to kind of rotate in the xy plane and the xz plane, you could multiply, you know, perform one of these transformations and then perform the other. In fact, you could actually multiply these two matrices together and just make that your combined transformation for rotating in both of them at once. So far, we've talked about reflections, scaling, and rotating. There's another type of movement that we might want to do for two-dimensional objects and three-dimensional objects, and this is translations. Let's talk about translations in two-dimensional space. You know that when you learned about graphing back in an algebra class, you learned about graph transformations, and you know, translating an object is like moving it horizontally or vertically. A lot of times that's like the first one you learn about, and I've actually saved it for last this time. So let's suppose we want to move an object to the right. Well, maybe to the right is not very precise. Maybe I should say in the positive x direction. Anyway, we'll draw a picture of the xy plane, and we'll move it in the positive x direction 2 units. So again, my example object is going to be in quadrant 1. It's going to be a box or a picture. I want to move all of its points to the right 2 units. So it winds up moving, and the new resulting object lands over here. Makes sense, right? So let's say we want to find the linear transformation that does this kind of action. And let's say we want to find the standard matrix of that linear transformation. There's actually a problem here, and this is why I've saved this one to talk about now. Do you see what the problem is? Can you guess what the problem is? Like, the question that I'm posing is, what is this linear transformation? We have a problem here, though. Every linear transformation must have t of 0 equals 0. That's a property of linear transformations. This doesn't look like it has that property. It looks like my point at 0, 0, the lower left corner of my picture, actually got moved to 2, 0. So it seems like it's not a linear transformation. It might still be a kind of movement that we would like to do, but I'm going to say that we can't find a linear transformation t from R2 to R2, or a 2 by 2 matrix A to do this. Maybe there's some other way to do this, but it can't be done like that. So there's more to talk about. That's not the end of the story. In general, suppose we want to shift delta x units to the right, and while we're at it, delta y units up. Let's say we want to be able to shift horizontally and vertically. There is a trick that we can do. We convert each point x comma y in R2 to a corresponding point x comma y comma 1 in R3. Then apply the transformation t from R3 to R3 defined by t of x equals ax, where a equals, well, I guess I'm just going to tell you the matrix here. 1, 0, delta x, 0, 1, delta y, 0, 0, 1. Okay. we're still talking about translations in two-dimensional space, right? Like a two-dimensional square that I drew and I want to move it to the right. And the trick is that we would take all of the points of that square and find the corresponding points x comma y comma 1 and apply this linear transformation. And this is a linear transformation. It's a matrix transformation, right? So you could actually verify that this does send the 0 vector to the 0 vector. So everything is fine. Let me show you an example of doing this trick. Our square that we drew just a few minutes ago earlier has these corners, right? The letter P written in it. Let's say the corners of this are 0, 0, 1, 0, 0, 1, 1, 1. It has these points that we could think about wanting to shift to the right. We want to move it 2 units right. So we'll use the matrix 1, 0, 2, 0, 1, 0, 0, 0, 1. So my delta x is 2, my delta y is 0. Let's try this on some of these points, some of these 4 points that are the corners of the box, okay? And let's see if it actually does what I say it does. So for the point 0, 0, the lower left corner of our square, the transformation should be applied. We said that the trick is you change x comma y to x comma y comma 1. That's what the trick said. So this should be this 3 by 3 matrix times this vector 0, 0, 1. This matrix multiplication is not very hard. It has a lot of zeros in it. I'm just going to tell you that if you do this, you wind up with 2, 0, 1. Now let me just show you something up above. I said that we convert each point x comma y to be x comma y comma 1. Now that we got the result, we convert it back. Just take the first 2 coordinates and say this corresponds to the point 2 comma 0. We basically get rid of the 1. Just ignore the 1. So my point 0 comma 0 did get sent to 2 comma 0. That's what we wanted. We wanted it shifted 2 units to the right. If you try this on a different point, here, what point am I doing here? The point 0 comma 1. Let's do this one. 0 comma 1 comma 1, right? You put an extra 1 there. You take this 3 by 3 matrix and multiply it by 0, 1, 1. And you do, in fact, get 2, 1, 1, which corresponds to the 2-dimensional point 2 comma 1. Which, if you look back at the picture I drew of it getting shifted 2 units to the right, this is exactly where we wanted this point to end up. 0 comma 1 moved to 2 comma 1. So I'll just say, etc. All of the points in our 2-dimensional object, whatever they may be, they do get shifted 2 units to the right by doing this. It's an interesting trick, right? Because for a second there, it seemed like we were in trouble. Like, wait a second, we can't find a linear transformation to do this. And that would be a shame because all the other transformations that we wanted are linear transformations. So this is a trick that lets us perform these translations shifting around using a linear transformation and matrix multiplication. This trick, what is the trick really? Essentially we added an extra coordinate of 1. We apply a linear transformation to it, and then we remove the 1 from the answer. So this trick of using x comma y comma 1 is known as homogeneous coordinates. The transformation is called an affine transformation. Now, I just want to be clear about something. Strictly speaking, this is not a linear transformation from R2 to R2 because it doesn't send the origin to itself. But it is still a transformation, even though it is not linear. So if we think of this as a map from R2 to R2, it's called an affine transformation. It's not linear. All of this was about doing shifting left or shifting right or shifting up or shifting down, but that was in two-dimensional space. So let's expand this to talk about translations in 3D space. Well, I went into detail for the two-dimensional version so that we don't have to go into all the details for the 3D version. But I'll tell you that the basics of it are we convert x, y, z to x, y, z, 1. And we use the matrix. It's actually going to be 4 by 4. And it's going to be 1, 0, 0, delta x, 0, 1, 0, delta y, 0, 0, 1, delta z, because we might want to shift in the z direction, and then 0, 0, 0, 1. So very similar to what we did above, except now we could shift along the x-axis, y-axis, or z-axis, or more than one of them at the same time. So I guess we've talked about 4 kinds of transformations, right? I guess, did we start with reflections, and then we did scaling, and then we did rotations, and then we did translations? So 4 different types of things that you can do to 2-dimensional objects or 3-dimensional objects. What I'd like to talk about for the remainder of the lesson is, what if you want to do multiple transformations? At the same time. So suppose we have a 3D model. This could be for like a 3D animation for a movie or a video game or anything. And let's say that it has 100,000 points. Okay, that's pretty reasonable. That's pretty typical for some kind of 3-dimensional object in 3D graphics animation. And let's say that we want the following done. In my example, let's say I want to enlarge by 10%. I want to translate 3 units along the z-axis. And let's say I also want to rotate 90 degrees counterclockwise in the XY plane. So lots of things are happening to this object all at once. In fact, I need to apply this to all 100,000 points. So 3 transformations. So each one of these is a transformation. Each one of them is a type of transformation that we've talked about today. And we could do, one way that we could apply these 3 things is T3 of T2 of T1 of X. 3 transformations being applied. Notice that I wrote 3, 2, 1. The reason I did that is because order of operations says you do what's in the parentheses first. So my first transformation, enlarging by 10%, is T1. So first I enlarge by 10%. Then I want to translate 3 units along the z-axis, and then I want to rotate 90 degrees counterclockwise. So T1 happens first, then T2, and then T3. Here's an idea. Let's find the matrices, and then set up A3, A2, A1, X. Because that's how we're going to apply these transformations, just by multiplying by the corresponding matrices. Again, I have them in the correct order. This is the order that I wanted. And that would do all 3 of the things that I wanted done. Here's a big idea. We can find A3, A2, A1 as one matrix. You know, matrix times, they're all the same size, and we multiply them, and let's say that the product of all of them is A. Then apply this one matrix A to each point instead of separate transformations. Because I said that this object has 100,000 points, and we're trying to do 3 things to each point, so it's a lot of work. This could save us time if we find the matrix A first, just find it once, and just, you know, write it down or store it or whatever, and then apply A to point number 1 of the 3D model, point number 2 of the 3D model, and so on. And it's easier than multiplying by A1 and A2 and A3 every single time. You just have one matrix instead. Now, there is a potential problem. Are these matrices the same size? I think a moment ago I said they were the same size, but it seems like A1 and A3 are 3 by 3 matrices, but A2 is 4 by 4, right? Because we said that for translations, we were doing that trick of homogeneous coordinates. We were doing that trick where we add a 4th coordinate, and just a few minutes ago, we wrote the standard matrix, and it was 4 by 4. So the solution to this potential problem is we make all of them 4 by 4 and use homogeneous coordinates. for all of them. That's going to allow us to do all these transformations in this way. So for three-dimensional graphics, a lot of three-dimensional graphics stuff is done using 4x4 matrices for this reason. By the way, computers like powers of 2. Computers are very good at dealing with powers of 2, so a 4x4 matrix seems convenient anyway, instead of 3x3. All right, so we're actually going to go through this. Remember those 3 things that I said that we wanted to do? Let's figure out these matrices. So T1, I said we want to enlarge 10%, and this is in 3D. You remember the 3x3 matrix that we said? So if we want to enlarge 10%, it's going to be 1.100, 0, 1.1, 0, 0, 1.1. Where did I get this from? This is because we had that matrix that looked like this: K0, 0, 0, K0, 0, 0, K. And it's sort of, how much do you want to enlarge by? We want the object to become 1.1 of its original size. But we want to do the 4x4 case, so what we're going to use when we add that extra coordinate of 1, we simply start with the 3x3 matrix that we had. And that 4th coordinate, we just have a 0, 0, 0, 1 in the lower right. And that's going to work. Oh, by the way, sometimes, we were talking about points in 3-dimensional space being x, comma, y, comma, z. When you add that 4th coordinate, sometimes it could be referred to as w. If you need a letter for it. You might not need a letter for it at all if it's always going to be 1. All right, so that is T1, or the matrix that corresponds to T1. And then for T2, we want to translate 3 units along, I think I said the z-axis. All right, earlier we had the matrix of this type of transformation. It looked like this. It's mostly 1s, but there's a delta x, delta y, delta z. That's what we're going to use here. So simply use the 4x4 matrix, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 3, because we want to move 3 units. It's a positive 3, so we're moving 3 units in the positive direction along the z-axis. That's going to be our 4x4 matrix. The 3rd transformation I said we wanted, T3, is going to rotate 90 degrees counterclockwise in the direction of the xy plane. We could figure out the matrix for this. So the 3x3 version, we said earlier, was cosine theta, negative sine theta, 0, sine theta, cosine theta, 0, and then 0, 0, 1. So in 4x4 case, with homogeneous coordinates, we know cosine of 90 degrees, and we know sine of 90 degrees. It's a very nice angle to work with, right? Cosine of 90 degrees is 0, and sine of 90 degrees is 1. So we can fill these all out with actual numbers, and we don't need to have theta. We know what theta is, so go ahead and evaluate sine and cosine. And this is going to be our 4x4 matrix to rotate a three-dimensional object 90 degrees. Let's keep going with this. We found all the 4x4 matrices. I said we want to do all of these. So let's make the combined transformation. A3, A2, A1. That's what these three matrices were. So I did this matrix multiplication. I'm not going to show every step of it. Has a lot of zeros in it. That's nice. Makes the multiplication a little bit easier. And you know, 3D graphics, this would be done by a computer, right? So we're doing this by hand to kind of understand it. All right, these were all of our 4x4 matrices. I multiplied them all out. I get a 4x4 matrix. The 4x4 matrix that I get, I'm just going to call it by A, the combined transformation, and it was 0, negative 1.100, 1.1000, 1.130001. All right, finally, we got it. So I guess you could say that using this 4x4 matrix, this kind of transformation with homogeneous coordinates, it would do those three things to a set of points in three-dimensional space. So multiply the 100,000 points of our 3D model by this matrix A. Of course, you wouldn't do it by hand. You'd have a computer do it for you. How about this? There's actually a nicer way to do this, maybe. Set up a 4 by 100,000 matrix. Capital X, where each column is one of the points. Then do A times X. This actually performs the transformation to all of the points at once. It's a very big problem. What are the sizes of these matrices? So A is 4 by 4, and X is 4 by 100,000. If you multiply this out, the result that you get is a matrix that is 4 by 100,000, and it is the set of points that have been transformed. It's the result of, you know, what were the three things we did? We enlarged by 10%, we translated 3 units along the x-axis, and we rotated 90 degrees counterclockwise. Do this, and you did all 3 of those things to all 100,000 points. So computers and graphics cards need to be very good at fast matrix multiplication. Yeah. Yeah, so this is happening. This is going on behind the scenes. Like anytime you play a 3D video game, you know, objects are being rotated and scaled and transformed, and right, all of these things are happening all at once to hundreds of thousands of points. The reason that I say video games are a really good example is because in a video game, you might need the game to run at 60 frames per second. And if you want transformations to be happening, you want objects to be rotating and stuff like that, and you want the game to run at 60 frames per second, then the computer needs to be really good at this, right? Computer needs to be really fast at doing all of these transformations. If it's something for a movie, it could be all kind of rendered. It could take, you could leave it rendering overnight or whatever, and then wake up in the morning and you've got the final product ready to go. But for a video game, you can't sit around and wait. Like, it needs to be ready a 60th of a second later. So, yeah, graphics cards in computers are designed to just do lots and lots of fast matrix multiplication, especially for this 4x4 case, because it's especially tailored to be able to do 3D graphics. And 3D graphics need 4x4 matrix multiplication to be done really well. So yeah, anytime you see 3D graphics being rendered, there is a lot of matrix multiplication happening under the hood. And that is why we also have a separate lesson about efficient matrix multiplication, which I told you, that's a really interesting topic of how can you multiply matrices really fast and efficiently. So I think we're going to wrap things up here. All right, so that was our lesson on an application of linear transformations and matrix multiplication. And yeah, 3D graphics. I think it's a really cool application. I don't think I mentioned this at the beginning, but this topic I don't think it's covered in our textbook. This is just kind of an extra topic that I came up with myself because I think it's interesting and it uses some of the tools that we've learned about this semester. All right, so that's going to be it for today. Everyone take care.